Hi, good morning, everyone.
Good morning.
Good morning.
How's everyone doing?
Stressed out.
Stressed out. You have exam midterms coming up?
Well, we have a take-home one going on, and also we have the election going on. So that's
Oh yeah, election. Did you guys vote?
I
Yes.
can't personally, but I hope everyone did.
Okay, yeah. So hopefully it's gonna be fine. Either way, let's see. I was very stressed last time during election. This time I'm like, yeah, let's see what happens. I can't do much anyways, except one vote. That's all I can do. Cool. Okay, so something you might have received email from Jocelyn last night. Did you or not?
I didn't receive an email.
Okay, so it's okay. So she's working on your homework. She said the grades will be ready tomorrow, Wednesday. I gave her the email address, the email address that sends an email to all the students in class, but it was not sure if it works. It looks like only I can use that to communicate with all the students and not anyone else except the instructor of the course. So anyway, so she just wanted to update everyone that she's working on these and the grades will be ready tomorrow anytime. Okay, so she's gonna email you back. The other thing is that the time of the second midterm, okay, so I look at the calendar and I think the November 19th is going to be the Tuesday of the Thanksgiving week. Thursday is Thanksgiving. On Tuesday, I think it's a good day to have the midterm. Then you have the midterm, you have the Thanksgiving break, then you come back, we will cover a few more topics, and then we're going to have the final. Okay, so the midterm is going to be on the 19th. The material are everything from chapter 1 and 2 complete, and chapter 3, everything that I'm teaching until the end of the Cartesian coordinates for the separation of variable. So basically the stuff that I'm teaching today will be in the midterm, but the stuff I'm teaching on Thursday and next week, they are not in the midterm. Okay, so that's how I'm separating this so that you don't have the last minute material to cover for the midterm. Okay, so these two announcements, midterm on November 19th, I'm gonna send an email as well. And the other thing is your homework grade will be ready on tomorrow. Sounds good?
What's gonna be the format of the test of the midterm?
Yeah, that's so what kind of format can we have? Okay, so it can be online or it can be more like traditional exams. Okay, so what I want to do is that I'm going to decide. I decided to do it more like traditional. So I'm going to give you 3 questions. You will have the entire time on Tuesday to do it and then submit it. Okay, you don't do the video and there's not going to be peer review. You just write it and send it back to me. Very similar to the exam that you would have taken right here. Okay, and of course it's open book, open notes. Sounds good?
What chapters the midterm will cover? Chapters 1 through 3?
1, 2, and most of the 3. Not all of the 3, but most of the 3. Yeah, until the spherical coordinate in separation of variables. Okay, so the stuff I'm teaching today will be in the midterm, but the stuff I'll be teaching next week, definitely not in the midterm.
Thank you very much.
Sounds good? So let me open up the chat. Only 1 midterm. Do you like 2 midterms?
Yeah, we're talking another midterm on.
Yeah,
on
I had 2 midterms last year for this course, but that was a weird midterm. If you remember, 2 years ago, we had a situation during the final week, there was threat and they had to cancel the final exams, if you remember that. And after that, what we did was, I only had a second midterm the week before the final. And the goal of that midterm was, in case the final gets canceled out, I have enough evaluation from all the students, from all chapters of the book, so that I can still give them a fair grade. Okay, but this year's situation is totally different. So I thought one midterm is good, and then you have assignment and quiz as well. So there will be enough evaluation points to give you a fair grade for this semester. Sounds good? Any more questions? Okay, so let's continue the chapter 3 and the separation of variables. I had started one example on separation of variables where we had the potential specified on certain surfaces, and we were looking at the solutions for the Laplace's equation that come in the form of the multiplication of two different functions in a specific way, and that is one function is only a function of one variable, the second function is only a function of the second variable. Okay, so this way you can really separate the functions, you can separate the variables. And in the form of the Laplace's equation, we said it simplifies into two ordinary second order differential equation. And if you have ordinary differential equation, the main advantage is that there are general solutions and you can use those general solutions, okay? So I'm gonna start that example, okay? And I'm gonna recapitulate what we discussed on that. And this is important, this is very important because it's the very first example on separation of variables, and this is one of those methods you can only learn by doing example, okay? There is no general way of teaching that, okay? So I want you to focus on this that I'm doing now. It's the first example I started last time. And then I'm gonna do a second example, which has a lot of common things with the first example, but also there are differences as well. So as I do the second example, I hope that you get much better insight on how we use the separation of variables. And then hopefully I have time to start a similar method, but using different coordinate system where we have different type of general solutions, okay? So let's get started, okay, and we go step by step. So the example was example 3.3 from the textbook. Okay, and the example was a situation that we have kind of one slab, something like this, and then another one. Right here. This is Z, imagine this is X. And this is Y. All right, it's not as easy to draw things on the board, but I hope it's a good picture. So what we have here is that we have two surfaces on the top and bottom. Each of them expand all the way to infinity on the X and Z direction, okay, but not going to the negative X direction, okay. So what we have is boundary conditions. Electric potential is 0 on the top. Electric potential is 0 on the bottom, and on this side the electric potential is V0y. That means it's a function of y. This axis is y, and that changes as a function of y. We have this boundary condition. This is not specified, so it can be any general type of function as a function of y. And then you will see that no matter what function it is, as long as it has a good behavior, it does not. As long as it has good behavior, it does not go to infinity or negative infinity, we always can come up with a set of solutions that we can use to match this boundary condition as well. So to boundary condition 0, this boundary condition is specified. If we go all the way to infinity on the x-axis, potential is going to be 0 as well. And that's because of the kind of limitations we have here. Okay, so the question is, what is the electric potential inside this slab? Okay, so we have the boundary conditions here, and we want to try to find the electric potential inside the slab. Here, we do not have any specific charge distribution anywhere whatsoever. Okay, so what you can imagine is that you can imagine the top surface is a plate, the bottom surface is a plate. Potential 0 means these plates are connected to each other and connected to ground. Okay, so electric potential is going to stay at 0, and this is, imagine, is a plate not directly connected to the top and bottom, but you just specify electric potential on this. Okay, so you can imagine these are conductors. Okay, the question was, what is the electric potential inside this slab? Okay, so we said for such problems we can use separation of variables, and that means we assume that V, which is function of x, y, and z, can be written in terms of one function x, which is only function of x, times y, which is only function of y, times z, which is only function of z. Okay, so this is going to make things a lot easier. Now, I want to remind you that separation of variable as a method doesn't work all the time. Okay, for certain problems it works, for certain problems it doesn't, but when it works very beautifully. Okay, and this is one of those situations. Okay, so we can simplify things a little bit because everything extends on the z-axis all the way to infinity. The problem is symmetric with respect to z, so the solution at the end should not be dependent on z, so we can reduce everything to v of x and y. Potential is going to be the function of two variables, and that can be written as xx times yy. Okay, that's how we can write the solution. And if we look at the Laplace's equation, which is second derivative of v with respect to x plus second derivative of v with respect to y equal to 0, if we use this v in this equation, we're going to come up with two sets of differential equations. And the way it happens is that v is function of v is x times y. If we take the derivative with respect to x, y is going to be a constant. So the first term becomes just y times d2x over dx2. Okay, and the second term becomes x times d2y over dy2 equals to 0. Okay, so what you can do is that you can divide both sides by v. That means dividing both sides of this equation by x times y, and then what we get here, we get, instead of y, we get 1 over x, and instead of x here, we get 1 over y. Okay, and if you look at this is very special and interesting in the sense that the first term is only function of x, the second term is only function of y. Okay, and that means two functions independent of each other. If you add them up, they are 0. Okay, so the only way it can happen is that either both of them are 0 or both of them are constants in a way that if you add the constants, they're going to be 0. Okay, so I'm going to say this one, let's say is C1, and this one, let's say is C2. Situation should be such that C1 plus C2 is always 0, and these two needs to be constant. Okay, you can, otherwise there's no way you can have a term as a function of x plus another term as a function of y always being 0. Okay, and that is where we can really separate equations and come up with different equations for the x and for the y. Okay, is it clear so far? This part is important because this is the fundamental steps for the separation of variable method. Okay, so if we separate these two, I'm going to say each of them is a constant. The way I want to write the constants, I'm continuing here. I want to say 1 over x times d2x over dx2 is k squared, and 1 over y times d2y over dy2 is negative kx squared. Okay, so what I did is that I already assumed that the constant for the x function is positive and the constant for the y function is negative. Okay, you could have done the other way around, okay, but depending on the situation that we have and the type of boundary conditions that we have, one of them works, the other one doesn't work. Okay, so later on you will see why I chose positive for x and negative for y. Okay, and another way of writing this equation, so here I have 1 over x. It's easier to move this term to the other side and make it like this, x of x, and do the same for y, this negative of y. Okay, so we have these ones, and now we want to solve these equations, and also the solution should meet the boundary conditions as well. Okay, so let's specify what type of boundary conditions we have here on the top. Okay, so what I want to do is that I want to get rid of this, and I want to list the boundary conditions that we have here. Okay, so the first boundary condition we have on the top, second one we have on the bottom here, v should be 0, so I want to write number 1, v should be 0 at y equals 0. Number 2, v should be 0 at y equals a. Number 3 is that potential v should be v0y at x equals 0, right? So this plane on this side is at x equals 0, and this is the boundary condition that is specified here. And number 4, v should be 0 at x goes to infinity. Okay, when x goes to infinity, we are very close still to the surfaces with potential being 0, but we are away from this, so the potential naturally should decay all the way to 0. So we got these 4 boundary conditions, okay, and we need to come up with solutions that matches those boundary conditions. The solutions of these 2 equations definitely satisfy the Laplace's equation, right? Because these equations are directly from the Laplace's equation with the assumption that the solutions can be separated into 2 functions of x and y. Okay, so now the nice thing, as I said, is that these 2 equations, there are general solutions for them, and these are the ordinary differential equations, and they are nice to deal with. So the general solution for x here, x of x, is a to the power of kx plus b to the power of b times e to the power of negative kx. Okay, so we have 2 fitting parameters, and this is the solution of this. For y, the general solution is y equals 1 constant sine of ky plus d cosine of ky. Okay, so these are the general solutions we have. And then if you multiply these, the general solution for v becomes vxy. Following this, it becomes 2 terms, e to the kx plus b e to the negative kx times c sine ky plus d cos ky. Sounds good? Now, what we can do is that we can simplify this a lot, okay, by just looking at the boundary conditions, okay? So I would first look at the boundary condition number 4. V potential should be 0 when x goes to infinity. Okay. Now, if you look at this, the second term coming from y is an oscillating term in terms of y. Okay. But if you look at the first one, this is function of x. And if x goes to infinity, the second term becomes 0, the first term blows. Okay, the first term becomes infinity. And we don't want that. We are looking for the solutions that if you go to positive x infinity, it becomes 0, right? So for this one, I would say A needs to be 0, and that's following boundary condition number 4. So I'm going to write in parentheses number 4 here. Okay, so A just disappears, this term just disappears as well. And then we have another boundary condition at y equals 0, v should be 0. Okay, if you look at the second one here, here we have oscillating functions c times sine ky and d times cosine ky. Sine is 0 at 0, okay? So at y equals 0, the first term here is 0. The second term here is non-zero at y equals 0. And we don't want that because we want to enforce the solutions that at y equals 0, potential becomes 0 as well. Okay, so the second term must be 0, and it means the constant d should be 0, and that is based on the boundary condition number 1. Okay, so two boundary conditions. If we put A0 and D0, we already meet the two of the boundary conditions, keeping the rest of things as general. Okay, now there's one more boundary condition. V must be 0 at y equals A as well. The sine function, we said, is good in the sense that at y equals 0, it's always 0. Okay, that's a good thing. But how about at y equals A? At y equals A, sine ky can have any possible number between 1 and 0, between -1 and 0. But we really want to only keep the solutions where v becomes 0 at y equals A. And that means that puts certain limit on the value of k. K cannot be any number. K can be only certain numbers that the sine of ky becomes 0 at y equals A. And that means k should be some value, something like this, n times pi divided by A, and can have any values of from 1, 2, 3, and so on. Okay, so k cannot be any random number. K can be pi over A, or k can be 2 pi over A, 3 pi over A, and so on. Okay, so there are only specific values k can have. And with those values, we can satisfy boundary condition number 2. Okay, so with this one, I'm going to just write 2 and say this is boundary condition number 2. Okay, so with these things, we could meet 3 boundary conditions. This we could meet by assuming d is 0. The last boundary condition we could meet by setting A equals 0. And the second boundary condition we could meet by saying that k can have only specific values. Okay, so what we are doing is this. What we started by the Laplace's equation. We separated and said v is like x times y. And then we listed the boundary conditions, and we are trying to narrow down the general solutions in a way that we are meeting all the boundary conditions. If we can come up with a solution that meets all the boundary conditions and satisfies Laplace's equation, that means we came up with the answer. So far, we did a good job because we know that this satisfies the Laplace's equation, and we could satisfy 3 out of 4 boundary conditions. So we are so close to really finishing this, okay? So let me summarize and write now a short version of this general solution after we said A equals 0, D equals 0, and K like that, okay? So let me get rid of these now. And say V of xy, okay? So the first term is 0, so I only have b to d e to the negative kx. b times e to the negative kx. And d is also 0, so I only have c times ky times c times sine of ky. K can have either of these numbers, and that's going to be n pi y divided by a. Okay, so this is a solution that satisfies the Laplace's equation and satisfies 3 of these boundary conditions. Okay, now b and c are constants that we need to find based on the boundary conditions, and that is the only boundary condition left here. Okay, so I can write it in a nicer way because b is a constant, c is a constant, so why don't I just use one constant for each of them? And so I'm going to rewrite e to the negative kx here. And by the way, k is n pi over a, so I can write it as e to the negative n pi x over a. Okay, and then here I want to use one constant, which is c, and c has to be determined in a way that it matches this boundary condition as well. Okay, so now there is one trick here. Okay, so this we said satisfies the Laplace's equation. Okay, so what if I come up with 2 equations, one of them having c1 and the second one exactly the same c2 times all the terms here? Both of them satisfy Laplace's equation. Okay, and you know, if one equation, if you have Laplacian of v1 equal to 0, and then if you have Laplacian of v2 equal to 0, right? You can add them up. The Laplacian of v1 plus v2 becomes 0 as well. Okay, so if you have a series of solutions that satisfies Laplace's equation, any linear combination of those solutions should satisfy Laplace's equation as well. Okay, of course, when the solutions are going to meet the boundary condition, you will have one specific unit solution, but this is still sort of the general solution with unspecified constant here. Okay, so in general way, this is not the only solution, but you can write it as a summation over many of these solutions with different values of n, that I can write as Cn times e to the negative n pi x over a times sine n pi y over a, and over this set of solution every xy. Now this is the real general solution for this Laplace's equation, and so this satisfies Laplace's equation, and this general solution already satisfies 3 of the 4 boundary conditions we have. Okay. Any questions so far?
So you mentioned that the general solution is just the addition of all solutions that we got from.
Yes. You can have a linear combination of these that I noted like with the sigma, and as long as each of them satisfies Laplace's equation, the linear combination will satisfy Laplace's equation as well. Make sense?
Yeah.
Okay. And it's important to remember that this not only satisfies the Laplace's equation, this is a simplified form of the general solution, which satisfies 3 out of 4 boundary conditions as well. Okay. So what we need to do for the rest is that we should come up with a way that this solution satisfies the boundary condition number 3 as well. And that's a little bit of work. That's more complicated than the rest of the equations, that which was only setting a specific constant at 0. Sounds good? Is it clear so far what we did and where we are going? Yes? No? Okay. So now we need to work on this boundary condition, which is at x equal to 0. Okay, so let me get rid of this. And I'm going to rewrite this at x equals 0. And that makes things simple because at x equal to 0, this term is e to the power of 0, which is 1. So at x equals 0, I only have the summation of Cn times the sine functions. Okay. So v at 0 and y is summation over n. The Cn constants times sine n pi y over a, n goes from 1 to infinity. Okay. And this is exactly the boundary condition that we want to meet there, and that has to be equal to V0 y. Sounds good? So what we need to do for the rest is we should find the Cn values. Okay, we should find the Cn values, C for each n, in a way that if you do this summation, the result be V0y. So if we can specify the Cn values, we are done with that. And we can use that here, and that solution meets Laplace's equation and all 4 boundary conditions, and then we are done. Okay. So now this has very specific format if you look at this. This is constants, amplitudes of sine functions added in a series, and we are setting that equal to one function. Okay. Are you guys familiar with Fourier series? And in fact, it's a Fourier series. Okay. And there's a theorem that says that if you have the Fourier series of infinite number of sine or cosine function, you can fit every possible function, the well-behaved functions. Okay. And that's a good thing because if we are here, we know that so there should be definitely solutions on the way we should specify Cn values and then meet this boundary condition. Okay, so now, do you remember what was the trick to find these the coefficients of Fourier series?
You just plug it into the like formula, right? For the it's like e to the power of something.
Well, we don't have e to the power of something. You could have you can have Fourier series in the format of e to the power of -i, and that's already a combination of sine and cosine. Here we only have sine, okay? But the basic trick is that to find Cn, what you do is that you multiply both sides by another sine function, exactly looks like this, but you use n prime. And then you integrate both sides in a way that for this side, everything becomes 0 except one term, that n is equal to n prime. And then Cn stays on one side of the equation, you will have an integral from the other side. And that way you can find every Cn value. Okay, let me do that, and then you will see what to do. Okay, so this is what we want to make possible. Okay, so what I do is that I multiply both sides of this by sine of n prime pi y over a. Okay, so this is exactly the same format of the sine function, but different n values that I'm specifying as n prime. Okay. And then if I do that, I need a little more space here. Let me see what I can do. So let me write this general solution small on the top, and I will use the rest of the board for that. So.
Professor, I have a question for the part you just wrote, x sine, that n pi y over a, is that n prime
This
Or
is
is
n
it,
prime, yes.
so does that mean that's a derivative or that's just this another
It's
n?
just another sine function that I want to multiply by both sides of that.
Okay, cool, okay.
Okay, so I'm going to multiply this by both sides and then see what we get. We get sigma n from 1 to infinity. We get Cn sine n pi y over a and sine n prime pi y over a. On the other side, I get V0y times sine n prime pi y over a. Okay, so far I just multiplied this. And now what I want to do is that I want to integrate this from 0 to a dy, and also integrate this side from 0 to a dy. Okay, so I multiplied both sides by sine n prime py over a and integrating it from 0 to 1. And now see what happens. If n and n prime are not equal to each other, the whole integral on this side becomes 0. Okay, so this integral is non-zero only when n and n prime are exactly the same. Okay, so out of this integral, considering we have a sigma here, we just get one single term out of that. Okay, and that is so let me move, so let's do this so that it becomes more clear. I can move the sigma out of the integral, right? I can also move Cn out of the integral because it's not a function of dy. Okay, so I'm going to write this as sigma from n to infinity Cn times the integral from 0 to a of this. Okay, and this integral as a whole is always 0 except when n is equal to n prime. So it's 0 for the values that n prime is not equal to n, and this actually turns out to be a by 2 when n prime is equal to n. Okay, so this is what we get from this integral. And because we have a summation, we are technically summing all the zeros and only one term non-zero here. Okay, so the left-hand side of the equation becomes Cn for the values that n prime is equal to n. Okay, for the rest it's 0. Okay. And the right side of the equation, it becomes V0y times, because now we are choosing only the n prime that is equal to n, here we get V0y times sine n pi y divided by a dy integral from 0 to a. Okay, so now if you look at this, this is technically the Cn values that we're interested in. And then here we have V0y, the function that was specified on this boundary condition. And the last term is sine n pi y over a. Pi is pi, y is the value of y that we're integrating here, and a is defined as y. So technically, with this integral, we can find all the values of c, like c1, c2, c3, and so on.
How did you make the Cn equal that?
So because here, out of the summation, we only have one term, right? And then this is only the right-hand side of the equation. The only change I did, I'm just picking up the n primes that are equal to n. because that's the only thing that matters.
Okay, but what happened to the integral part on the left side?
The integral part on the left side is always 0,
Okay,
except when n prime is equal to n.
okay. And how come that didn't make the whole left side 0?
Oh, because we have summation here, right? We have one summation, so we have one single non-zero term, which becomes just this.
Oh, okay.
And by the way, I have here a divided by 2, so I need to put 2 by a on this side. Okay, and this a by 2 is this integral only for one of the values of n primes. Sounds good? So basically, this combined with this gives us a solution that meets all the boundary conditions and satisfies Laplace's equation. Right now, we cannot make this more simple than this because V0y is not a specific function, it's a general function that's given to us. But with this integral, you see that everything is specified. So you can really put like n equal 1 and calculate this if V0y was given. Okay, so I'm going to continue this with the special case that V0y is just a constant. Okay, V0y is a constant V0, and then with that, we can simplify this more. Okay. So far, so good. Is it clear? The whole approach. It's a long approach, and it's one of those things you just need to learn it once. And of course, as usual, it's one of those things that I want you to sit on your textbook, read it step by step, and reproduce that, have a pen and paper in hand, and do it a couple of times, okay? I can tell you, even when I want to teach this, okay, I've done this many, many times. Still, when I want to prepare for teaching this, I do that from beginning to end myself to remind myself and learn all the steps. It's a beautiful method, but as you see, it's not that simple. It's not complicated either. Once you learn it, you will see the concept. It just flows, but you should really do it on your own.
Professor, I have a question.
Sure.
How is it that when n prime is not equal to n is equal to 0, but when n prime is equal to n is equal to that constant, how do you conclude to that?
Oh, okay. So these are two sign functions, okay? And when you are integrating from 0 to a, you are technically, look at the y value, okay? You are changing it from 0, what you have inside, to n pi, which is an integer multiplication of pi. Okay, so if n and n prime are not 0, you are technically multiplying functions that have the form of this, and if you integrate them, they become 0. Okay, the sine function from beginning to end, one whole cycle, that becomes 0. Okay, now if n and n prime are the same, what you're doing is that you're integrating the sine to the power of 2 functions. So you're integrating a function like this.
Oh, okay.
Like this. A function that is always positive. Okay, that only happens when n and n prime are exactly the same. And that gives you something non-zero. For the rest of the terms, from all the way from 0 to from 1 to infinity values of n, that becomes just 0, because you have functions that have positive and negative in a way that integrating over one full period, that makes that 0.
Okay, so basically you just solve the integral and figured out at what parts the whole problem becomes 0 and when it's non-zero.
Yes. So technically this integral is always 0 except for the special case that n prime is equal to n.
Okay, oh, okay, thank you.
That was a good question, because that's important, how we can go from here to here, left term being complicated, left-hand side being complicated term to the point that it's only Cn values. So and that is the common trick in Fourier transform, okay? When you want to find the coefficients, that's common. You always do that. You multiply that by sine function. If it was cosine, you would have multiplied that by cosine function.
So that was just by just plugging in A into Y and figure out where it's non-zero and where it's zero?
Yeah. So that's the trick, to isolate Cn from the summation and the sign function and come up with an equation that we can really evaluate what should be all the Cn values. Sounds good?
Yeah.
Okay, so what I want to do is that I want to continue with the assumption that V0y is a function, is a constant and not a specific function of y anymore. Okay, so let's do that. And I want to show you how you can simplify things a little further. So I want to keep this general solution here. I want to get rid of this, and I want to keep that as well. So for the special case that V0y is V0, the Cn values, that integral becomes 2V0 over A, the integral from 0 to A. Then we have sine n pi y over A dy. And if you look at this function, this integral, this becomes 0 for even values of n, and that becomes non-zero and that is two over n pi, 2a over n pi for odd values of n. Okay, so if v is 0, if v0y is v0, we can move that out of the integral, that becomes 2v0 over a. Okay, and this integral for n pi y over a dy, that becomes 0 for even values of n. Okay, and that becomes 2a over n pi for odd values of n, and then the whole Cn becomes 0 for even n and 4v0 over n pi for odd values of n. Okay, so this is the Cn values we get if we want to meet a boundary condition that v0 y is a constant v0. Okay, so if you look at the boundary condition, okay, we will have a situation that I'm really going out of space here, so I'm going to erase this. Okay, so the general solution with all these constants and everything becomes 4 pi 4v0 over pi, the sigma, because all the even values give 0, so n can be 1, 3, 5, and so on. And this is 1 over n from this sum times the first sum here is exponential term into the negative n pi xa. The second term is a sine function, sine n pi y over a. Okay, so this is now the solution for V0 y being a constant. Okay, so as you see, the solution at the end must be in form of a summation. Okay, and that is the only way we can fix and meet the boundary condition on x equals 0. Okay, and if you put x equals 0, the first term is 0, and you will have a summation of 1 over n times sine n pi y over a. Okay, you have that summation, and that is how you can, that's technically a Fourier series that can meet a constant value. Okay, so your textbook has a nice demonstration of how that summation can, with all the values of 1, 3, and 5, and all the way to the end, can really make a sine function, a series of sine function, meet a constant value. Okay, so I'm going to try to reproduce that a little bit. Maybe not as good as the figure in the textbook, but that's going to give you a feeling why we need this summation and how this summation really adds up to come up with a constant function. Okay, so let me get rid of this.
Professor, where did you get the 1 over n from?
The 1 over n from this term, that Cn is 4v0 over n pi. And 4v0 over n pi was
it's in the
constant.
front.
I moved it out of the summation. 1 over n is inside the summation.
Gotcha. Thank you.
Now, let's look at V0 y, which is the value of the potential on this boundary condition, which is supposed to be 0. Okay, so if we look at this, we have 4v0 over pi, summation over n equal 1, 3, 5, and so on, of 1 over n times sine n pi y over a. Okay, so if you only use the first term, that's going to be like a sine function. Okay, if I plot that so what we want is that we want function v0 from 0 to a. Okay, so we are trying to reproduce this function, which is a constant from 0 to a, by this summation. Okay, if we use only the first term, we get something like this, which is part of the sine function. Okay, so this is what we get when we use n only equal to 1. Okay, if you include n equal to 1 and 3, that means using 2 terms from this summation, what we get is a function that looks like this. Okay, if we use more and more terms, this summation is going to give us something like this. Okay, if we use all the terms all the way to infinity, we have this oscillation becoming smaller and smaller because we are using the higher values of the sine terms with higher frequency, in a way that if we go really all the way to infinity, it's going to produce something like a flat function here and coming back to 0 at a equals a. Okay, so this is how a combination of sine functions with specific amplitudes, if we add them up, they can create whatever function we want. Okay. Of course, if we did not have a constant v0, if this v0 had other forms at x equals 0, we still could use the Fourier transform to fit that, but then we needed to use a different type of coefficients here. Okay, you just change coefficient as a function of n, then you can fit different functions. Okay, so this is what Fourier transform can do with us. And when we use separation of variables, because we come up with general solutions that have sine and cosine into them, we need to use Fourier transform to make sure we can match all the boundary conditions. Some of the boundary conditions were easy, like 1, 2, and 4, but some of the boundary condition really depends on using a summation of x, y, summation of Fourier transform. Sounds good? Okay, so it's 10:26. So I really want you, and there's only way to learn it is that read your textbook, read step by step, so everything that I explained here, or you can watch the video of what I did here and try to reproduce that, have a piece of paper and a pen in a hand and do step by step, okay? And do that multiple times, and that's the only way you can learn this. Okay, any question? No, you're good?
I guess,
Okay. So what I want to do is that question.
yes.
For the third condition, why we ended up using the third condition? You said that it's because there's no way we can follow it up in terms of the Laplace equation.
Yeah. See, why did we use the third boundary condition? We have to use all the boundary conditions. Okay, so the solution should meet all the boundary conditions and should satisfy Laplace's equation. Okay, so now out of these four boundary conditions, let's say number 4, it was easy to come up with a solution that meets this one. We just said A equals 0 from the general solution, and we were sure that by eliminating A, we are meeting this one. Number 2 and 3, we did different ways, we did different things to satisfy these two. Number 3 was not easy because it was at x equals 0 and we had to satisfy that. Okay, so the only way to do that was using the Fourier series and using the whole linear combination of the solutions with the specific coefficients to meet this one.
Okay, so usually with these problems, you figured out the easy boundary conditions such that you get rid of most of the coefficients, and then you approach the hardest.
First, you do easy boundary conditions to simplify the general solutions that you have. Okay, use easy ones, simplify the general solution, and whatever left, then you gotta use Fourier transform.
Is it always Fourier transforms?
I mean, yeah, most of the time you need, at some point you need to use that.
Okay, thank you.
Yeah. When you use separation of variables for electrostatic problem, at the end, there's always a series like this at the end in the solution.
Okay, I wanted to ask something else. If you could refresh me where the B0 minus Cn came from on the left side of the board. B0 minus Cn.
V0 minus Cn. Oh, this is not, yeah, sorry. This is, I just said it's a.
Oh, okay. And that would be a different problem, right? Where
Yeah,
we're
but
given.
here I said if you put V0y as a constant, then Cn simplifies into this.
Got it. Perfect.
V0 can come out of integral, sit here as a constant.
Thank you.
Sounds good. Any more question? Okay. As I said, it's important. So expect something similar to this on the midterm. Okay, so what I want to do is that I want to start another example which has similarities to this and also differences to this as well. And that is example 3.4 from the textbook. Okay, so let me erase everything here. Okay, so this is the case that you have. So the previous example was a slab extending all the way to infinity. And this problem is a situation that you have something like this. Okay. Imagine you have rectangle shape like this, sitting at x equal negative b, x equal positive b, at the x-axis. This is y, this is z. And imagine this extends all the way to infinity as well. So this is only the cross section. Electric potential on this side being 0. Electric potential on this side being 0 as well. And on the top, oh sorry, electric potential on this side is being specified at V0. Here also a constant V0. On the top electric potential is 0, and on the bottom electric potential is 0 as well. Okay, so what you have a rectangular tube, you can imagine, extending all the way to negative infinity on z and positive infinity on z. On the sides, you have electric potential specified being V0 is a constant, and on the top and bottom electric potential is being 0. The question is, what is the electric potential inside this geometry? Okay, so we have this setting. The first step is identifying the boundary conditions here. Because the geometry here extends all the way from positive z to the negative z, at the end it's symmetric with respect to z, so everything is only function of x and y. Okay, so in a way we can look at the cross section in terms of x and y, and we have something like this, x and y. Something like this. Here potential is V0, here potential is V0, here V is just flat 0, and this is 0 as well. Okay, so we have this one extending on the z-axis all the way to negative side and also positive side as well. Okay, so can you guys help me? What should be the boundary conditions here now? Some of the boundary conditions are similar to the previous one, and some of them are a bit different. And here, imagine dimensions are from negative b to positive b on the x, and on the y, this is from 0 to a on the y. Okay, so one boundary condition at y equals 0, the boundary condition is that electric potential should be 0. Is that correct?
Yes.
Y equals 0, potential should be 0. So we have the same similar boundary condition that we had here. The next one is at y equals a. On the top, potential is being 0 as well. So that is again similar to what we had before. At y equals a, potential should be 0. And then we have boundary condition on the left and right hand side here on the x-axis. Okay, so at x equal to negative b, potential should be v0. So I'm going to change this, and I'm going to change this as well. So potential should be 0 at x equals negative b. And then we have x at positive b, potential being v0 as well. So I'm changing this. X equals b. So we have these 4 boundary conditions. Okay. Similar to the previous case, v is only function of x and y, so it can be written as x of x times y of y. Okay, and all the steps to set up and separate variables are the same as before. So the general solutions are the same. X should be a times e to the kx plus b times e to the negative kx. And y of y should be c times sine ky plus d times cosine ky. Okay, so general solutions are the same, but now the way we find the constants here should be a little different. Okay, so you remember previously we said a should be 0 because we have e to the power of kx, and e to the power of kx blows at infinity. Here we cannot say that because the whole boundary we have here is from negative b to positive b. We don't have anything to do with the x equal to infinity. Okay, so what we should do is that we need to keep all the a and b values. Okay, we can't just drop a because it goes blows at infinity. But one thing is that the whole problem is symmetric with respect to x. It's even with respect to x. That means if we look at this, whatever we have for a, which is coefficient of k to the x, we should have exactly the same constant for b, which is e to the power of negative kx. Okay, so because of the symmetry, a and b must be the same. Okay, so what I do is that I'm going to get rid of b and use a here as well. Okay, so for x, I want to say a times e to the power of kx plus a to the power of a plus a times e to the power of minus kx. Okay. And if I want to simplify this, that is basically a times e kx plus e negative kx. And that is 2 times cos hyperbolic of kx, which is a times cos hyperbolic of kx, or 2 times. Okay. So the x component could be simplified in this way, okay? So the y components, we have something similar to the previous case. D must be 0, okay? D must be 0 because of the boundary condition at v equals 0, okay? So we want v being 0 at y equals 0, so there's no other choice than setting d equal to 0. And for k, we have the similar limitation that it should be 0 at a as well. That means k should be n pi over a, with the n values being 1, 2, and everything else. So we simplified things a little bit, okay? We said because of the symmetry, here x function should be like had the form of 2 times a times cos hyperbolic kx. D must be 0, very similar to the previous example, and k must have only values of n pi over a, very similar to the previous example, okay? Now, if we rewrite the general solution, so far, we could simplify this to this one, that Vxy is cos h of kx times sine ky, and because of limitations on k, I'm going to write it in terms of n pi y over a. Okay, and then I'm going to just use one constant here, and I'm going to call that c. Okay, so basically the constants we have here are 2 a's and c here, but they are multiplied to each other, so we can use just one constant. Okay, so again, if this is a solution, any linear combination should be solution as well. So I'm going to call that Cn, and sigma over Cn from n to infinity, and that is V x on y. And because of the k, I can write it in terms of n pi over a. So that is cos hyperbolic n pi x over a. Okay, so this is how much we could simplify things. It satisfies Laplace's equation because it's multiplication of x and y, and it satisfies boundary conditions at y equals 0 and y equals a. So these two are met. Okay, now we need to satisfy 3 and 4. Okay, now the nice thing is that we made everything symmetric with respect to x. That means number 3 and number 4 are kind of tied to each other. Okay, they are already locked to each other. So if we satisfy any of them, it's going to satisfy the other one as well. Okay, so the rest of the work that we need to do is that we need to find a way to satisfy equation number 4 or 3. Okay, and that way we can satisfy both of them simultaneously. Okay, so let's see what happens at the point of V, the boundary condition at V equals plus D. So at V of By, which is that boundary condition, the potential becomes summation from 1 to infinity Cn cos h n pi x over a times, and here x is b, so n pi b over a. So the whole thing is a constant independent of x, and second term is sine n pi y over a. Okay, and these should be equal to the constant V0. Sounds good? So this is the value of potential at x equal b. Based on this general solution, it has this form of this, but we know that has to be equal to V0. Okay, so what we want to do is that we want to use the same trick and somehow get rid of this, and that means we want to multiply both sides of the equation by sine n prime pi y over a. Okay, so I make one side V0 times sine n prime pi y over a, and make this side, these two terms are independent of y, so I'm going to write sigma n equal 1 to infinity Cn cos h n pi b over a, and here I have sine n pi y over a, and I'm going to multiply by sine n prime pi y over a. Okay, and these two are equal to each other. I'm going to integrate from 0 to a dy, and I'm going to integrate here from 0 to a dy as well. Okay, so the terms here are all independent of y, so I could take them out of the integral. So we have something like this, and that is very similar to the previous situation. Okay, so we are out of time. I'm going to stop here. Okay, and on Thursday, I'm going to start here and finish this example, and then we move on to the spherical coordinates as well. Any questions so far?
I have a quick question about the midterm, because on the 19th, I'm doing a presentation for my other class at 11 o'clock. I was just wondering what to expect of the midterm, how we'll take it, just so I can prepare so I'm not late for my next
Well, it's
class.
supposed to be within the class time.
Okay, okay.
So 10:45, we should be done.
Okay, okay,
And then
perfect.
the only thing you need to do is that you need to take picture of your midterm and upload it.
Okay,
So
sounds
hopefully
good.
that's going to be okay too.
Okay, thank you.
Okay. Sounds good. Any question on this? So my recommendation for you guys, before Thursday, read the example 3.3 and 3.4 very carefully, okay? And come back with questions if you have questions. Okay, that's important. I'm sure I will have one separation of variable question on the midterm, okay? So make sure you prepare really well for that.
So professors, for the midterm, so how is it going to work? I know I have to go over these problems, but I just want to know how the format of the midterm would take.
It's very similar to traditional midterm. So I'm going to give you 3 questions, okay? And questions are similar, not exactly the same, but sort of similar to the examples I do in class or the homework assignment that I give you, okay? So just if you know how to do them, you should be able to do the midterm as well.
Okay. And will it be time?
Yes, it is time, yes. So you do that during the class.
Oh, so we're gonna do it during class.
Yeah, you do it during the class. You have 1 hour 45 minutes to complete.
Okay.
Sorry,
Okay.
1 hour 15 minutes to complete.
Okay. Thank you, Professor.
Sounds good?
Yeah. Thank you, Professor.
Yeah, thank you.
Thank you.
I will send an email regarding the midterm as well, because I see not all the students are attending this Zoom session, so that others know that as well.
Thank you very much.
See you guys on Thursday morning.
See you Thursday
Yeah.
morning.